My name is Vlad Kostolev, and I would like to thank you for coming to our presentation on the solar resource mapping, monitoring, and forecasting using satellite data. I would also like to thank Dr. Hans de Kluner for his assistance in organizing this event. This presentation is co-authored by Green Power Labs Incorporated and Applied Geomatics Research Group. Green Power Labs is a solar energy assessment and consulting company based in Halifax, Nova Scotia, Canada. Established in 2003, the company provides services across a full range of solar energy deployment needs, from regional solar resource mapping to integration of solar systems for a particular site and task for a variety of customers. Our team combines environmental engineering and business development expertise. The Applied Geomatics Research Group is a part of Nova Scotia Community College's Centre of Geographical Sciences in Middleton, Nova Scotia, Canada. This is a team of research scientists, research associates, and graduate students applying a suite of geomatic technologies to explore environmental, health, and social issues. Now, today in this presentation, I will cover a range of topics, starting from description of satellite data and its use in solar climatology, the rationale for using geostationary satellites for monitoring of solar radiation. Then I will give some examples of satellite mapping technology applied in Atlantic Canada, its logic, the sequence of steps, ground truthing. I will describe the software that was developed by Green Power Labs, which is called SolarSat Data, and speculate about next steps and commercial applications of this technology. Now, the information on solar resources is commonly obtained from existing databases, long-term climatological observations and records, or from new measurements made by using often delicate and expensive equipment, such as pyranometers. Now, the satellite mapping gives an opportunity to have broad coverage for solar radiation mapping. Such maps of solar climatology and solar resources can be used to estimate electricity that can be generated by various solar energy conversion technologies, from grid-connected photovoltaic systems to concentrated solar plants, and it can be also used to plan for correct siting for new solar power sites. Here's an example of satellite-based solar climatology provided by NASA. Now, this map here shows a 22-year climatology from 1983 till 2005, which is based on integration of a number of data sets. In particular, the World Climate Research Program and International Satellite Cloud Climatology Project provided data which were used as input into the solar radiation calculations algorithms, and which were used to derive cloud information. Now, this surface meteorology and solar energy data set contains many solar parameters which are formulated for assessing and designing renewable energy systems. This particular screen grab is from Green Power Labs web mapping server, which shows the capacity of the server to display various types of information, such as global horizontal radiation, the ranges of it, direct normal radiation, diffuse, and so forth. Although the data set provided by NASA is available to public, the mapping of this data set was done by us, and it's unique to our company. The next slide shows a mapping of solar radiation in higher resolution. Now, the previous, again, I skipped mentioning that the NASA data set is 1 by 1 degree in latitude and longitude resolution. So it is pretty coarse. You can zoom into this data set by studying interaction between the solar energy flow and the landscape, and in particular, paying attention to shading provided by different landscape features. The features would remove a large proportion of direct solar radiation. So mapping interaction of landscape and solar energy flow is particularly important for concentrated solar power technologies for planning their siting and performance. Now, why would we need satellites? Why don't we just put our measuring devices around the globe and observe the availability of solar energy? Well, first of all, they require maintenance. They cost money. Somebody needs to take care of them and download information from them. Also, they have to correspond to certain requirements of World Meteorological Organization in order to be useful for solar radiation measurements. The chart to the right of the slide shows the percentage of complete observations of solar energy, of solar radiation in Nova Scotia. And for the last 30 years, there were only two stations which were recording solar radiation. And from 1994 until now, the number of observations decreased, and actually the measurements stopped just 5 years ago. I'm not sure about the reasons for discontinuing these measurements in our province, but I'm aware that across North America there are not so many consistent measurements of solar radiation. Satellites in this case provide a view from above of the Earth's atmosphere and surface, and the logic of measuring and calculating solar radiation from satellite imagery is very simple. The brighter the clouds above the Earth's surface, the more energy is reflected back to space, meaning the less energy is reaching the Earth's surface. The little chart in the left bottom corner of the slide shows the coverage or approximate coverage of the two geostationary satellites, GOES East and GOES West. Actually, they image the whole globe, but above 60 degrees latitude, the quality of the images and the resolution of the images is so low that it's not extremely useful for solar energy modeling. So such geostationary satellites are helpful because they're positioned at exact height above the Earth's surface, and they rotate around the Earth at the same speed. So virtually they remain at the same position in relationship to the Earth as they were initially. They also rotate at the same altitude, which is about 36,000 kilometers, and it's very interesting that there's this huge belt of satellites stretched around the equator, and I think the number of them is measured in hundreds, which coexist at the same altitude. Probably some of you have heard the news about the collision of Russian and American satellites recently, and the likelihood of that collision was less than the likelihood of another intelligent life in space. So it was very, very interesting for me to think about this coincidence and compare it to the density of geostationary satellites around the globe. Now, in addition to GOES satellites, there are other satellites run by different agencies and by different countries. Japan, for example, runs GMS satellite, which covers part of the Asia and Pacific. IODC is the Indian Ocean satellite, and there are many other satellites. So this information is available. The frequency of collection of this information varies. For GOES West and GOES East, the satellites take image every half an hour. For Meteosat, which covers most of Meteosat 2, covers most of Europe and Africa, the images are taken and transmitted every 15 minutes. IODC, I think, is transmitting at a much lower frequency, I think measured by several hours. However, each of these images is a valuable snapshot of the surface of the brightness of the clouds above the Earth's surface. Another reason to use satellites is that it is very difficult to interpolate between your observations when you map solar energy. It is common for scientists to take a number of stations and run statistical techniques such as kriging, or GIS capable people would use inverse distance weighting or splines or any other statistical routine which would produce a nice and smooth surface representing or modeling the assumptions about the distribution of solar energy flow. However, it was shown by several authors that you cannot meaningfully extrapolate and interpolate beyond the 25-kilometer distance from the meteorological station. Now, the whole idea of using satellites and the Earth cloud albedo and surface albedo for calculating energy flow is about 20 years old now. It was well described by Kano in 1986, and it was developed ever since by academia. In particular, Richard Peretz and his group are very strong in developing and applying this methodology in North America. I think the dataset, 10-kilometer resolution dataset produced by Peretz's group is available for free on the internet for those who understand how to use it and interpret it. However, satellites such as GOES Est and GOES East give you the resolution of 1 square kilometer in nadir, so it's 100 times better than the 10-kilometer resolution. And again, these images are available from NASA, and they can be used for modeling solar radiation, at least for our hemisphere. The advantage of using visible spectrum images is that following the methodologies of Peretz and Kano, you could pretty much avoid calibration of the satellite information. You just use image as it is, as a black and white photograph. Also, it was shown that the methodology is very robust, and it can tolerate minor errors in navigation of satellites and in georeferencing the satellite images. Another advantage is that after you have done your mapping and modeling of solar energy based on satellite imagery, only a small number of high accuracy ground stations is needed to ground truth and calibrate the resulting maps. So what we did with assistance of Industrial Research Assistance Program was to obtain a year worth of GOES East satellite images for North America. Our special interest was Nova Scotia, where our company is located, and we decided to apply the methodology, well, improve and develop further, and produce a solar energy map for Nova Scotia based on satellite imagery. While doing this, we adjusted the existing mathematical algorithms, and we tested our results against a number of field stations in Annapolis Valley, which are operated by our colleagues from the College of Geographical Studies, and we tested these observations. Now here are two examples. The large map in the back is the part of the GOES image for North America, and again, for those of you who are not familiar with the modeling of solar radiation from the Mars, you can easily see that the bright clouds suggest that they reflect the solar energy back to the observer, in this case to the satellite positioned at his geostationary location over the equator. On the right side of the slide, you can see Nova Scotia outlined under the clouds, and you can appreciate the scale of our province, which is located on the east coast of Canada. Sorry. Now, For any given location, we produce a cloud index, which is derived from image's pixel brightness in relation to the pixel's dynamic range. If you look at any place here which is covered by a cloud, by a bright white cloud, you can imagine that if the cloud wasn't there, the pixel would be much darker. The pixel brightness would correspond to the albedo of the Earth's surface. When the clouds are covering this pixel, then its value is much higher. By looking at these pixels through a sequence of images from let's say for a year's worth of images, we can establish the minimum and maximum values for the brightness. And then we can relate this brightness to the cloud cover. So the logic is, again, it's very simple. The implementation is not simple. This is why we're proud to tell you about this work. Again, in a nutshell, if we look at a particular point here, which is in the middle of Nova Scotia, we analyze a pixel which is 1 by 1 kilometer approximately. Well, actually, at this latitude, it's more than 1 by 1. It's about 1.5. We apply clear sky solar radiation model to this location, knowing the day and time and the year, and then we look at the dynamic range of pixel brightness in order to extract the cloud information for this particular location and the time. And as a result, we come up with the, sorry, I'll just drag this arrow here. There you go. We come up with actual model, which should be pretty close to the truth. Now, if you look at this image here, clear sky model just assumes what would happen there if there are no clouds. And the actual realistic model tells you that through the day, the solar radiation goes up and down depending on the cloudiness of the atmosphere. Okay, let's go to the next one. So let's look at an example, just one image being analyzed. This particular one comes from March 26, 2007, 15:15 UTC time. And you can see that there's a big band of clouds coming from New Brunswick through Nova Scotia into Atlantic Ocean. They're definitely brighter than the underlying ground. So how does this image relate to other images? Now, in order to establish the dynamic range of pixel brightness, we have to look at certain window of images surrounding the one of interest. Now, the images we look at are from the same day, from the same time of the day as the one we are analyzing, because we need to make sure that the relationship between the sun and the Earth's surface position is the same, and the sun and the satellite position are the same. So we take a 25-day window and we calculate the minimum and maximum values for pixel brightness. This image here shows the minimal pixel brightness. So this is the minimum albedo, which is assumed as the albedo of the bare ground in this case. This image shows the maximum value. So this is completely overcast sky, but this is an artificial image. This is not an actual photograph taken by GOES satellite. This is an artificial model of what the maximum albedo of each pixel within the area of interest was during the 25-day window. And you can see there's a certain pattern there, which appears because not every part of the study area was covered by clouds repeatedly. Some of the parts were cloud just once or twice, so you can see some texture to it, which may be a complication for the further calculations. Now, using these three images and a clear sky model, we can calculate solar power density for the particular image. So now that grayscale image turns into the map of solar radiation. The blue and reds here are low. You just refer to the little diagram color bar on the lower right side of the slide. Light yellow is high radiation. So at that particular moment, it was very simple. Where the clouds were present, the radiation was lower than where the clouds were absent. If we go to the next slide, here we summarized all of the slides, all of the GOES images for that particular day. Now, I remind you that we obtain images every 30 minutes. So there are a lot of images used for calculations right here. And as the cloud belt was going through New Brunswick and Nova Scotia, you can see that the total solar energy density was pretty smoothly distributed. Now still preserving this gradient from west to east. If we do the same for the whole month, we can see the spatial pattern much more clearly. Now we don't see the separate events, I mean separate clouds moving through the area. Now we see the long-term or longer-term climatology distributed over the provinces that we have studied here. And it's very interesting because we can see that in the, just let me grab my pointer, it's somewhere here. Okay, in the Prince Edward Island and Cape Breton and the northern part of Nova Scotia. Okay, there it is, right here. Radiation is much lower than in the southern part in general. Okay, so we did this process for all of the months of 2007, and we were very happy to see that we were not just picking the results of the clear sky model, which would suggest that, yeah, there's more sun in the south than in the north. And we could see that the spatial pattern of solar radiation was changing through the year, and it was really different in different months. So if you look at January here, for example, you have lower solar radiation in the Annapolis Valley, Cape Breton, higher along the Atlantic coast. But if you go to June, the pattern reverses, and you have more effect of rain and mist along the Atlantic coast here during the summer times because of the difference in temperature between the atmosphere and the ocean. And you have much higher radiation in the Annapolis Valley right here, which is known to be very productive agricultural area of Nova Scotia, where they grow a lot of apples and grapes and so forth. So that was one first happy discovery. Then you could integrate all this data and you could calculate the resulting annual average map of global solar radiation, in this case for the whole province. And you can use this map now to plan your management decisions about energy generation and energy distribution. In our province, most of the energy is generated in Cape Breton, in this area here, and the lack of energy is electrical energy is observed in the southwestern part of the province. And of course, you have to transmit this energy from here to there, incurring transmission and distribution losses. So if you think about deployment of solar energy, the most logical place to deploy it would be, of course, the sunniest part of this province. Well, this is just one of the examples of how the solar radiation maps could be used. Of course, we needed to ground truth our model, and we distributed a number of meteorological stations across the Annapolis Valley, that sunniest part of the province. And they were taking a number of meteorological parameters together with solar radiation, which was measured by using SP light sensors, which are Keep on Zone and pyranometers. And we used these observations to ground truth the model. Now, the discoveries were very interesting, first of all, because they worked, the model worked, and second of all, because it didn't work always consistently. And the first problem that we noticed was that in the winter time, our correlation between the model and the observations was pretty low. Whereas in the summertime, we were very happy. Actually, June and July are even better than May. And the best root mean square error for a monthly, for a particular month, for a particular station was less than 15%, and high correlation between observations and the model. Now, why didn't winter work well? Well, some of you look outside of your window, you probably would not see snow, but I do, and by this time Nova Scotia got more than 100% of expected snowfall for this particular year. And the snow is a big nuisance when you're trying to, sorry, I'll go back, when you're trying to analyze the albedo, because satellites cannot really, so visible spectrum image from satellite can't really tell you if you're looking at clouds or snow cover. And now let me skip 2 slides forward. Now, if you look at the pictures here, these are just some snowfall days in Nova Scotia in January 2007. This information is collected by Environment Canada, and again, it can be used for improving the quality of your model. So what we did later, we introduced these data layers in our system, and we improve the quality dramatically. So if this is normal processing without accounting for snow, the image in the bottom shows much better quality. By the difference in brightness, you can see that we have much more energy now, because we don't assume that the snow is clouds, and we don't account for losses which don't actually exist. Second thing which was important was accounting for turbidity of the atmosphere. This data is very important for concentrated solar power modeling and monitoring. And the turbidity basically is a generalization of the clarity of the atmosphere. However, the observations of turbidity are not readily available, and the resolution of the turbidity data set is not high enough to be used directly. Now, this is one of the improvements of the model we are working on. We obtained the turbidity data from for certain meteorological stations, and they are being now introduced to our model, again dramatically improving the results and the quality of the results. Now, if you look at the hourly changes in our model solar radiation versus the observations, there's a great correspondence as well. Some difference in these red and blue curves here, which one of them stands for the model, second stands for actual pyranometer observations, are mostly because pyranometer integrates data for every hour, and our model shows the values modeled for every half an hour from the pyranometer, from the satellite images. Of course, this methodology can be applied anywhere where we have, first of all, satellite coverage, and second of all, ground truthing stations, which we can use to improve the model. The most important part of our project was actually linking this whole modeling exercise to geographical information system. And we have established partnership with the ArcGIS in developing a plugin which now works within Arc and allows you to do all the tasks, starting from download through clipping of the areas of interest which you would like to analyze for solar radiation, to modeling of actual global horizontal radiation, accounting for snow, for differences in linkage turbidity, for presence or absence of water bodies, and so forth. Of course, because this is GIS, it allows you to have all kinds of contextual information together with your models, and the outputs, which are integrated daily, monthly, and annually, are readily presented together with information such as distribution of populated places, road networks, rivers, so forth. Just a snapshot of how the plugin installs the buttons in ArcGIS, and pretty much any user can click on these buttons and start his own calculations. Now, the mapping and monitoring are closely linked. When you download your Go satellite imagery every half an hour, it gives you power to actually monitor the availability of solar energy at any pixel of your image in near real time. Now, this is extremely important for tracking performance of power plants, for evaluating building energy demands, and things like that. And you can look at a number of potential clients interested in mapping, monitoring, and then forecasting of solar energy, which may not have a capacity or will or resources to install hardware at their site. Now, system like I described, can provide utilities with resource assessment. It can monitor the demand of power based on solar energy. It can also supply forecasting estimates. For energy traders, a system like this may help to develop strategy for trading. It may give information on assessment of volatility of energy demand. It may help forecasting supply and may help establish price, thereby facilitating future trades. Building owners may be interested in monitoring energy balance, for example, the heating demand, historical demand, future demand, and so forth. So there's a number of applications of this system, and what we're doing right now is implementing this new forecasting capacity based on the satellite model that we have developed and implemented, and this forecast will be working from both in high resolution up to 6 hours and in low resolution to 48 hours based on statistical information on cloudiness as well as on the analysis of cloud motion vectors. So even though I didn't talk a lot about monitoring, I hope that the message is clear that availability of satellite information allows you for near real-time monitoring of solar energy in any location. Forecasting is being done by different agencies and different academia scientists as well. There is no, as far as I know, there's no big consensus of how exactly this should be done. So this is still a research issue for many. However, we need a system in place which would provide forecasting capacity to utilities, energy traders, and users. Okay. This, in a nutshell, is my presentation for today, and I'm happy to leave some time for you to ask me questions, and I'll be more than glad to answer them. Thank you.